Hello everyone, this is the Mechanism Sessional Group project on windscreen wiper mechanism simulation. And the group members are I myself Talapalli Harvind Raj and my partner Akella Kalyan Lakshmi Srinivasa. Here you can see the problem statement. The problem statement is to stimulate the mechanism for the windscreen wiper with no quick return effect. You can see the diagram here. Now let us look at the two important terms related to this problem statement. First one, the quick return effect. It is a mechanism in which time taken by the forward stroke and backward stroke are different. But according to the problem statement, we assume both the forward stroke time and backward stroke time are equal. And the next term is Grashoff's criterion. In a 4-bar mechanism, there exists at least one revolving link if the sum of the lengths of the largest and the shortest links is less than the sum of the lengths of the other two links. And here you can see the formula. From here, my partner Srinivas will take on.
Everyone, I, Akella Kalyan Lakshmi Srinivasa, will now be taking over the problem statement solution approach. So, on the left, we see the 4-bar, the entire image of the problem statement. Now, from here, it is evident by moving point D, we can move the wiper. So, let us focus primarily on the 4-bar mechanism ABCD. On the right, we have an image of the 4-bar linkage ABCD. We have taken the lengths of AD to be L1, AB to be L2, BC to be L3 and CD to be L4 respectively. The links AD is the origin. Let angle AB, the angle between AB and AD be theta 2, the angle between CD and AD is theta 4 and the angle BC makes with the horizontal is theta 3. Now to perform displacement analysis, let us assume that point A is our origin and that AD lies on the x-axis. Then the coordinates of point B and point C can be obtained as L2 cos theta 2 and L2 sin theta 2 for point B and L1 plus L4 cos theta 4 and L4 sin theta 4 for point C. Now we know the length of link BC is L3 and we know the coordinates of points B and C. By applying the distance formula, we get L3 square to be L1 plus L4 cos theta 4 minus L2 cos theta 2 whole square plus L4 sin theta 4 minus L2 sin theta 2 whole square. Now, this expression upon expanding the right hand side can be simplified and written as A sin theta 4 plus B cos theta 4 is equal to C, where A, B and C are all functions of theta 2. So, what we are effectively trying to do is obtain sin theta 4 obtain theta 4 in terms of theta 2 because that will help us while doing the simulations. Now, for obtaining theta 4 in terms of theta 2, first we start with taking the half and tan theta 4 by 4 as x. Now, we obtain these expressions for the sin theta 4 and cos theta 4 and substituting them in this equation, we get a quadratic equation for which x has these roots. A plus or minus under root a square plus b square minus c square by whole divided by twice of b plus c. Now, since we know what tan theta 4, we know that x is tan of theta 4 by 2, we now obtain an expression for theta 4 in terms of a, b and c. On another note, we can also find tan of theta 3 in this method. We know the coordinates of points C and B and thus we can find the slope of point BC as the y coordinate of C minus y coordinate of B divided by the x coordinate of C minus the x coordinate of B. However, the slope is also the angle a line makes with the x-axis and in this case this angle has been stated to be theta 3 by our assumptions. Thus, tan theta 3 is this expression from which theta 3 can simply be obtained. Now, let us see how the simulation works in this slide. Our simulation was done on MATLAB. For this simulation, we started with a value of 0 for theta 2 and arbitrarily chose to simulate 10 simulations. However, the angle this makes is 20 pi radians, but there are an infinite number of points on the real line between 0 and 20 pi radians. So, to not have any problems, we chose a 720 uniformly distributed points, including 0 and 20 pi. Thus, each of our angles differs by 5 pi by 180 radians. This approach was inspired by the finite element method, which is a method to solve differential equations that most softwares these days use. Note that by increasing the size of the theta 2 array from 720 to say 7200 for example, the accuracy of theta 2 values, the accuracy of the simulation to its actual counterpart that we have derived analytically will increase. However, since this simulation takes time to run, by increasing the array, the simulation also becomes slower. Now let us look at the code before running the simulation to see how it works and showing what happens when we increase the length of the theta 2 array. So first we have defined the values of L1, L2, L4 and L3. As such, the value of 650 for L3 is obtained from the no quick return condition. Now L5 is the length of the wiper, and as stated before, we have chosen 10 rotations arbitrarily. Now we have defined the theta 2 array and then written code for theta 4 and then theta 5 and then theta 3. Now this is the code that starts the simulation. And now let us see what happens when we run the simulation. This is how the code runs. Now as it is evident, there is no quick return effect for the forward and the backward movements. Now what happens if we actually increase the number of values in the theta 2 array from 720 to 7200 by making this 5 pi by 180 into 5 pi by 1800. So I have chosen the 5 pi by 1800 value here. Let us run the code to see what happens. As it is evident, clearly the accuracy of the array has increased. Accuracy of the simulation. However, it is now much slower than the previous simulation. Similarly, by decreasing the number of values in the theta 2 array from 720 to 72 for instance, we can show that the simulation becomes much faster and much more haphazard. See how fastly it had run. Now let us run it again to show that it will run extremely fast and stop just as fast. So increasing the simulation length is a bit problematic. So let us keep it at 5 pi by 180. Now what if we remove the whole 5 factor? That again, this only changes the time of the simulation and the speed at which it runs and the accuracy of the code with the analytical approach, which is the most accurate one. So simply changing the values multiple times doesn't do much to our problem statement. Now let us return back to the presentation to complete the velocity and acceleration analysis. Now we are back in the presentation and we will be completing the velocity and acceleration analyses for this. So let us start with the velocity analysis. The velocity analysis was done using the method of ICs. To start with, we have 4 ICs already defined for the system by the A, B, C, and D at their own locations. Now we have defined I13 and as point after finding it out. Now what we did is we found the lengths XA and XD. For XA, we used the value of tan theta 3 and expanded on it, while for XD, we simply use the sine rule in triangle X, C, and D. And from that, we obtain these specific values for XA and XD. XA is L1 sine of theta 2 minus theta 3 by sine theta 3, and XD is L4 sine theta 4 minus theta 3 whole divided by sine theta 3. Now, why have we found these expressions? Because because I13 is an IC, it should have the same velocity with respect to its corresponding links, being AB and CD in this particular case. Thus, the velocity of X with respect to AB will be theta 2 dot into XA, and for the velocity of X with respect to CD will be theta 4 dot into XD. And since we have already found XA and XD, we get this equation from which we get theta 4 dot as j theta 2 dot. This j is called the Jacobian and is defined as XA by XD, where X, which comes out to be L1 sine of theta 2 minus theta 3 by L4 sine of theta 4 minus theta 3. Let us move on to the acceleration and torque analyses. So, to start with, the acceleration analysis is simple. We have the velocity analysis expression as theta 4 dot equals j theta 2 dot, and we differentiate this expression. Now, on differentiating this expression, we get theta 4 double dot equals to j dot theta 2 dot plus j theta 2 double dot. We've simply used the product rule in this step, and for this step, we have used the chain rule. Now, with that, we get theta 4 double dot is del j del theta 2 plus j del theta 4 whole into theta 2 dot squared plus j theta 2 double dot. Since we already have an expression for j in terms of theta 2 and theta 4, and since we know the relation between theta 2, theta 3 and theta 2, theta 3 and theta 2, theta 4, we can easily obtain the values for del j del theta 2 and del j del theta 4. Let us move on to the force analysis. For finding the force analysis, we have made one assumption, and that is that no energy is lost in the whole process. That is, the input power supplied to the crank AB is completely spent on rotating the rocker CD. By using that up, now for any rotating system where the rotating torque is tau and the rotating angular velocity is theta dot, we have the power as tau times theta dot. The power is a dot product between the torque and theta dot to be. And by our assumption, this power is not wasted at either AB or CD. Thus, the power at AB should be equal to the power at CD. However, by sign convention, the power is lost from the system at CD and comes into the system at AB, and thus we get this thing to be our power expression. So, theta 2, which is the output torque, is equal to theta minus theta 1 into theta 4 by theta 4 dot by theta 2 dot by theta 4 dot. Now, if we look at the velocity analysis, we will find that theta 2 dot is into j is theta 4 dot. So, theta 2 dot by theta 4 dot will be 1 by j, which is what we have written as j inverse. Thus, the output torque and input torque are related by the Jacobian again, with the output torque being 1 by Jacobian times the input torque. That is it for our presentation. Thank you for watching the whole video.